time you'd have to have 1, comma, 2, comma, 4 to hit that one. To hit this one, just 1, comma, 4. To hit this one, just 1, comma, 3, comma, 4. So you can't hit all 3 targets at the same time. Why is that happening? The best way I can understand it so far is that when you do everything in terms of Boolean algebras, there's a characterization of the tri-commutativity that involves taking two subalgebras and taking their union and taking the subalgebra generated by those. And that comes up in tri-commutativity, but not in bicommutativity. And the issue is then, what is the exponential functor doing? Well, you can have 2 subalgebras, they generate a bigger algebra, yet if you apply the exponential functor, you get 2 subalgebras whose union does not generate the exponential of that bigger earlier algebra. So that's my best understanding on why is this happening at cubes and not at squares. Just digging into some Boolean algebra on that. And coming back to the proofs, in the converse direction, to go from a retract, to go from a big commutative inverse limit of finite discrete spaces to getting that you're a retract of the power 2, use this characterization that says, okay, you're this big subspace essentially of 2 to the kappa, and if we look at some restrictions, say, to initial segments, where you project down to the alpha, then you can ask, okay, I want to have a bunch of, actually, the key word here is open. I want to have open surjections, where I have, say, at the restriction to, I guess the projection to 2 to the alpha plus omega subspace of that, then you want to project down to, say, just 2 to the alpha. Right? Then okay, so that's what the times 2 to the omega is about. You have these little countable gaps between the lengths of these initial segments, and when you make that projection to forget a little countable piece at the top, you want to have it be an open map, not just an arbitrary quotient map. So if you can rig it that way, get it inside 2 to the kappa in that form, then you're good. And it goes on. A key point, you have to argue that because you've got a commutative diagram of, say, k plus 1 cube of finite surjections, you can actually bump that up to an open quotient map from something at the top of that k plus 1 cube that actually an inverse limit of countably many of them. You use a bunch of elementary submodels, and at any stage you only have to deal with, at most, n big pieces of the past, say, if you're talking about weight Aleph n as your goal. And this was known for a long time that if you have a bunch of open maps and all maps between finite discrete spaces are open, and you take a bicommutative limit of these open maps, the limiting map is also open. So you bump stuff up from finite to open maps between second countable compacta. So we have all these second countable quotients here. And then you use some elementarity, and then you get that, okay, the quotient from all the stuff through stage aleph plus 1 to all the stuff through stage alpha is open. And then you're done. And I have some open questions. Can't really tell the difference between 3 commutative and 4 commutative yet. I think they should be different, and I can prove that if we're talking about open maps between second countable spaces. But if we're talking about just finite surjections. I haven't been able to actually show that there's a difference between equaling some limit of tricommutative cubes of finite surjections and equaling some limit of finite surjections with 4 commutative 4 cubes. So I'd like to know about that. And there's some related questions. They all require you to cook up something weird of weight at least alpha 3. And in at least one situation, I have 2 questions where I know the answer is yes, but to one of them, possibly both of them, but I don't know which. It has to do with, there's a chain of 2 implications that I know is strict, but I don't know which of the pieces is strict, possibly both. So, yeah, there are some questions. Question 2 here is exactly what is the difference between tricommutative limits of just these finite surjections and tricommutative limits of second common Boolean spaces. More broadly, I would like to know, are there other interesting properties, extra requirements we could put on these inverse limit diagrams of finite surjections and characterize other interesting classes of spaces? So I will quit there.
Thank you. Any questions? I just have one. I suppose this is absolute no transfer independence on these.
Oh no, I'm using these Davies sequences, so this is all ZFC. Everything I said is ZFC.
But your questions, can you prove your questions?
I've wondered about that. Maybe I can cook up something with a morass, but I haven't yet, right?
Okay. Okay, well, let's thank the speaker.